Welcome to Pre-Calculus, Section 3.3, Finding Zeros of a Polynomial Using Long Division. I'm splitting this lesson into two parts, Part 1 and Part 2. Each of them will be approximately 30 minutes long. So the first concept that we want to make sure we understand is something you guys have heard many times. So let's go over these ideas here. The first idea here, a real number C is a zero of P. So let's pick a number. Let's say x is equal to 2 is a zero of some polynomial P of x. Okay, so we're saying that. An equivalent statement would be that P of 2 is equal to 0, meaning that if you plug 2 into your polynomial P of x, you should get 0 as an answer. Okay. The other thing that it says is that x is equal to c is a solution to the polynomial P of x is equal to 0. All right, so that says the same thing. If you put 2 in the function P, it should give you a true statement. 0 equals 0, meaning 2 is a solution to the function P of x. Okay, the other equivalent statement is that if x is equal to 2 is a 0, then x opposite sign 2 is a factor of the polynomial P of x. All right, and the other equivalent statement is that the point 2, 0 is an x-intercept of P of x. All right, so this graph illustrates that. So if 2 is a 0, then you've got the point 2, 0 lies on the x-axis. It is a solution, is an x-intercept, and it is a 0. Sometimes also you'll hear it called a root. Okay, and then the most important thing that we're going to deal with today is that if you've got a 0, x is equal to 2, you have a factor x minus 2. All right. All right, so we're going to solve this problem here. It says find all zeros of the function f of x given. Also given that x is equal to 2 is one of the zeros. So if x is equal to 2 is one of the zeros, then according to what we just said, x minus 2 is one of the factors of this polynomial. Now, given that the degree is 3, we can have a max of 3 real zeros. I'm not dealing with complex zeros yet. All of the functions I give you in this unit are going to have real zeros. So you have a max of 3 real zeros, and it could be less if you have multiplicity going on. All right, so we're given one of the zeros here. All right, now let's think about a number problem so we can understand what we're going to do next. If I'm told that 2 is a factor of 12, and I divide 12 by 2, I'm going to get a 0 remainder because 2 divides into 12 evenly. What I also know is that I'm going to get the other factor when I divide 2 by 12 because we know that 2 times 6 is equal to 12. So if I know one factor and I divide, then I'll uncover what the other factor is such that 2 times 6 is 12. All right, we're going to apply that same principle to polynomials. If I know that x minus 2 is a factor and I divide by x minus 2 into my polynomial, what you have left on top in your quotient position will be another factor of that, the other factor of that polynomial. And you'll also see that you'll get a 0 remainder when you perform that division. So let's try that. All right, so I set it up. Now we're going to do the division. So what do I need to multiply x by to get 6x cubed? So that would be 6x squared. So 6x squared times x is 6x cubed. 6x squared times negative 2 is negative 12x squared. So I'm going to subtract. So I've got 0 here. So negative 1x squared plus 12x squared is 11x squared. I'm going to bring down my negative 18x, and I'm going to divide again. What do I have to multiply x by to get 11x squared? So that would be 11x. So 11x times x is 11x squared. 11x times negative 2 is negative 22x. So I'm going to subtract. So I'll get 0, and negative 18 plus 22 is 4x. I'm going to bring down my negative 8. So I'm going to ask myself, what do I have to multiply x by to get 4x? And that would be 4. So 4 times x is 4x. 4 times negative 2 is negative 8. So this looks promising because when I subtract there, I'm going to get an r of x is equal to 0, which is what we said would happen if x minus 2 is a factor of f of x. You would expect it to divide into f of x evenly, which means you would have 0 remainder. So what that tells me is that the other factor is 6x squared plus 11x plus 4. So let's look at what I wrote here. So if x minus 2 is a factor of f of x, then x minus 2 times the quotient plus r of x should give you f of x, but we know that r of x is 0. All right? So we've got this function now broken down into two factors. So what we also know is that 1, 0 is x is equal to 2. So this function over here must give us the other two zeros. I should say this factor, 6x squared plus 11x plus 4, should give us the other two zeros. So the first thing I'm going to check is to see whether I can break this down into two other factors by just factoring a quadratic. If not, I'm going to have to use the quadratic formula. So 6 times 4 is 24. So the ways to make 24 by multiplying, I'm going to write down, 3 times 8. That one looks like it might work, and then it would be 4 times 6. So 3 times 8 is 24, and 3 plus 8 is my middle number, 11. So this looks to be factorable. So since I have a leading coefficient of 6, I'm going to factor it by parts by putting 3x plus 8x in the middle to represent 11x. So I'm going to factor it by parts. So you guys know how to do this already from Algebra 2. All right, so I factor this and I get 2x plus 1 times 3x plus 4. Okay, so from this factor I've got 2x plus 1 is equal to 0, so that's 2x is equal to negative 1, x is equal to negative 1/2, second 0. Now I've got 3x plus 4 is equal to 0, 3x is equal to negative 4, x is equal to negative 4/3 is the other 0. So I found 3 real zeros for this function f of x by dividing by the factor given. We were given a 0, we turned it into a factor, and finding another factor, and then taking the second factor, breaking it down into 2 more factors, and from those factors I was able to finally find the other two real zeros. Okay, let's do example 2. So the wording says find all zeros of the function f of x given this function. So as I've mentioned, the problems in this unit have real zeros and not imaginary zeros. So the degree of this function is 3, so we could have potentially the maximum number of 3 real zeros. There could be fewer if we have any multiplicity. But the difference between this problem and example 1 is there aren't any known zeros. We don't know what any of them are yet. So I'm going to show you a method that I teach, and that is a topic that we teach in pre-calculus, but in this online version of pre-calculus, we don't have quite as much time to spend on each of these topics. So I'm going to go over it relatively quickly. So rational zeros, meaning rationals are ratios of two integers, q and p in this case. We're going to figure out what potential ratios q over p can we test to find out whether they are zeros, to give us a starting point with knowing 1, 0. So the way that we do this technique is we look at the leading coefficient here, and the constant here. Okay, so this is the p end of the equation, and this is of the function, and this is the q end of the equation, or the function. All right, so we look at the factors of this 1 here. There's only one factor of 1, so I have one factor. For 8, so I'm not looking at the signs, I've got 1 times 8, and 2 times 4. So I'm going to list those 4 factors of 8. 1, 2, 4, and 8. Okay, so in order to make q over p ratios, I'm going to do it systematically. I'm going to take each of these q's and going to put it over, in this case I only have one p, so there aren't going to be that many possibilities. There could be more depending on whether you've got a number here like 6 or something that has more factors than just 1. Okay, so this is a relatively simple example here. So I'm going to find my q over p's, which I'm going to then test to see if any of those are zeros, so I have a starting 0 to deal with here. Okay, so the first one I'm going to have is 1 over 1. So 1 over 1. The next one I'm going to have is 2 over 1, q over p. The next one would be 4 over 1. And the next one, 8 over 1. And then because we know that they could be any combinations of pluses or minuses in order to come up with negative 8, I'm going to put plus or minus on all of these. Okay, so I have 2, 4, 6, 8 potential rational zeros to test. Now, because that 1 under there doesn't matter, let's just get rid of it. All right, so a potential 0, if any of these nice, neat numbers are indeed zeros of my function f of x, they would have to be plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. All right, it would be one of those. Could be more. There's up to 3 real zeros for this. Okay, so then the technique is that you test each one of them out. You plug it in and you see if you get 0. So there's a lot to test. And I would go all the way down to the last one being f of negative 8. And I want to find one that gives me 0, and I'll say, okay, that's a starting point, that's a 0. So I did that, and I found that f of negative 8 is 0. So f of negative 8 is 0. So that implies that, so I substituted negative 8 into my function f of x, and I got 0. I said, okay, that means x is equal to, well, let's just write it all out. X is equal to minus 8 is a 0, which means that x plus 8 is a factor. Okay, so now I'm back where I was on example number 1, where I have a known factor now. Okay, so this is an analytical technique, and there are others. Polynomials have a lot of things we can do with them, but we don't have a whole lot of time to get into them as much depth as you might in another course further on. But now we have a factor. Now there is another way to do this, and this is a way that I don't like, and this is by typing the function, the polynomial, the original polynomial, into Desmos and seeing if there is a place where you can read the 0 as an exact number on the x-axis. And there it shows up, that negative 8 shows up here. Okay, now these right here are just decimal approximations. And when you're doing this unit and when you do it on a quiz, we want exact answers, which means they're going to have to be either whole numbers, fractions, or combinations of radicals, fractions, and whole numbers. But decimal approximations are unacceptable. All right, so now we've got a starting point, and we're going to do the process that we did in example number 1. Okay, so I erased that other stuff. So now we've determined that x is equal to minus 8 is a 0, which implies that x plus 8 is a factor, which implies that if we divide x plus 8 into the function, we should have a 0 remainder. So I set it up. So we're going to divide x plus 8 into my function f of x. We expect to get a 0 remainder, and we expect to uncover the other factor, which would be the quotient on top. So let's go ahead and carry out the division. So what times x will give me x cubed? So that would be x squared. X squared times x is x cubed. X squared times 8 is 8x squared. Subtract. So we get 6 minus 8 is negative 2x squared. I bring down negative 17x and I divide again. What times x gives you negative 2x squared? That would be negative 2x. Negative 2x times x is negative 2x squared. Negative 2x times 8 is negative 16x. Now I subtract, and I get 0. Negative 17 plus 16 is negative 1x. And I bring down, then I divide again. So what times x gives me negative x? So that would be negative 1. Negative 1 times x is negative x. Negative 1, negative 1 times 8 is negative 8. And I subtract, and I get 0. Okay, so we did reinforce that x plus 8 is a factor because it divides evenly into f of x, and we've uncovered what the other factor is. So what I've written down here is that f of x is equal to d of x, our divisor, q of x, times q of x, our quotient, plus r of x, which in our case is 0. So this is what we have now. So from here, we know this one gave us our 0, x is equal to minus 8, and this will give us our other 2 zeros. So we want to see if it's factorable first. So we've got negative 1 times 1 is negative 1. There's only one way to make 1. I need one negative. So I can't get negative 2, my middle number, by adding with only one negative, so it's not factorable. So I'm going to have to use quadratic formula on this one. All right, so I'm going to say negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. So Carrie, let's move over here. So we've got 2 plus or minus the square root of 4 plus 4 over 2. So that's 2 plus or minus the square root of 8 over 2. 2 plus or minus 2 root 2 over 2. So cancel, cancel, cancel. So our other two zeros are 1 plus root 2 and 1 minus root 2. So just to summarize, we started out with this function with no known zeros. We used the idea that if there is a rational root in this for this function f of x, it'll be of the form q over p, and I showed you how to test each of those numbers to find out if any one of them will give f of that number equals 0, and we found that f of negative 8 is 0, and that means that negative 8 is a 0 of our function, which means that x plus 8 is a factor of our function, which means if I divide by x plus 8, I should get a 0 remainder, and then uncover what the other factor of the function is. Once I know that other factor, I can rewrite my function as x plus 8 times that factor. And I know that x is equal to minus 8 is 1, 0. So this part, the other factor that we just uncovered, is going to give me the other two zeros. If it's not factorable, I use quadratic formula, which I had to do in this case, and I found out my other two zeros. So that's the process. So that's the end of this first video. The other two example problems are going to be in part 2 for section 3.3.